So, welcome you all in my next lecture. So, this lecture my plan is to talk about Bayesian. I will introduce the notion of what do I mean by Bayesian. But in my last lecture I talked about like mixed derivative theorem, that means if the mixed derivative exists when they are equal. So, those theorems I have discussed, and then I talked about couple of examples that even if there are some conditions on the mixed derivatives. See, suppose mixed derivative is not continuous, in some examples the mixed derivatives becomes equal, and in some example you have seen that they are not equal. So, today I will talk about Bayesian, and then mean value theorem. We will see what is the notion of concept of mean value theorem in kind of functions from Rn to Rm, in particular functions from Rn to R, that means scalar field. Then later I will talk about Taylor's theorem for functions of two variables, like Taylor's theorems you know for single variable calculus, you know the notion of Taylor's theorem. So, similar sort of concepts available in the context of vector valued functions of vector variable or in particular scalar field. So, that is the kind of plan for today's lecture. Okay. So, as I said, so my plan is to talk about Bayesian, the notion of Bayesian. Okay. So, in my last lecture I talked about mixed partial derivatives and their equality, and couple of examples I have discussed. Now, I will introduce the notion of C1 function, C1 function. So, this is the notation C1. Now, in single variable calculus, so I should write C1. So, in single variable calculus, suppose you have a function f from say R to R, suppose you have a function f from say R to R, okay, and suppose your function is differentiable. Now, once my function is differentiable, then derivative I can think about it is also a map from R to R, right. Suppose you have a functions from R to R, it is differentiable at all points in R. So, therefore, derivative is also a map from R to R. Since derivative is a map, so therefore, I can talk about the continuity, whether the derivative maps, that means a prime, whether it is a prime means what? It is a map, that means x goes to a prime of x. Okay. So, for example, if I have a functions from R to R, how it acts? X goes to f of x, right. Now, if my function is differentiable, that means derivative is also a map from R to R, okay, and what is the map? X goes to a prime of x. Now, if I say that my functions f is differentiable along with that derivative map is continuous, then I will say that f belongs to what is called C1. That is called single variable functions. Now, if I have a function instead of R to R, suppose I have a functions from Rn to R. Now, the question is, can I talk about the notion of C1? Answer is yes, because given a functions f from Rn to R, I introduce the notion of partial derivative, directional derivative and total derivative, right. So, there were similar sort of notions I can say. Yes, I will say that my functions from Rn to R, if my function is differentiable, of course, the notion of differentiability I already talked about that, I mean total differentiability, and if the derivative, I have to think derivative should be a map from Rn to R, so that means it should be continuous. So, if I have that one in the context of Rn to R, then I will say that f is C1. More precisely, this is the one I have read. So, let S be an open subset of Rn. Suppose you have a functions f from S subset of Rn to R, and suppose I am saying that all the partial first order partial derivatives exist for all x inside S. Therefore, the corresponding first order partial derivative is also a functions. So, that means if my functions from Rn to R, so therefore, how many partial derivatives you will get? First order partial derivatives, n many partial derivatives you will get, because you have a Rn, that means n many directions are there, n many independent variables are there. So, therefore, I can talk about del f, del x1, del f, del x2, del f, del xn, and each di of f is a map from Rn to R. Since each di of f is a map from Rn to R, so therefore, I can talk about the continuity of those functions. What I am saying is that suppose you have a functions f from S subset of Rn to R, suppose all first order partial derivative exist, then I can think about my first order partial derivative is again a map from S subset of Rn to R, okay, S subset of Rn to R. That is I have written if dfi is a map from S to R, that means x goes to dfi of x if it is continuous. So, that means I assume that suppose you have a functions f from S subset of Rn to R, suppose all the first order partial derivative exist. Now, I am thinking first order partial derivative as a map from S subset of Rn to R, and if all the first order partial derivative continuous, or then I will say that my f is said to be continuously differentiable on S, in short C1. Now you can guess why it is continuously differentiable like in the single variable case. That means first my function should be differentiable and derivative is continuous. Here what I am assuming, I have a functions from Rn to R, or f is a map from S subset of Rn to R. What I assume is that first order partial derivative exist and they are continuous. Now if you remember, I already kind of discussed a theorem that there is a sufficient conditions for differentiability or existence of total derivative. If I have a functions from Rn to R and if all the first order partial derivative exist and continuous, then my function is differentiable, and that exactly I have assumed that each first order partial derivative they are continuous. So therefore by sufficient condition for differentiability, I can say that my function is differentiable, that means total derivative exists. And not only that, you can write your derivative. What is your derivative in that case for this kind of functions? Your total derivative, if you check, is total derivative at the point x naught is nothing but the gradient of f at x naught, if you see. In other words, derivative of x you can write as del f del x1 at x up to del f del xn at x, or in terms of, I will say that d1 f at x up to dn f x, correct? So now since the first order partial derivative exists and continuous, that means my function is differentiable, of course, and derivative is also continuous. Why? Because my derivative is nothing but the first component is the first order partial derivative with respect to x1 up to the nth component is nth order partial derivative of f with respect to xn variable, and each of the partial derivative is continuous. And you know, if I have a function whose n components, that means if I have a function say f which I represent as a n components and each component function is continuous, that means my function is continuous. So that means in that case also my function is differentiable, that means total derivative exists, and this is also continuous because each component is continuous in the hypothesis given. So therefore I will say that yes, if these things happen, that means if all the first order partial derivative exist and they are continuous, then I will say that f is said to be continuously differentiable on S, and in short form I will write C1. 1 stands for once continuously differentiable. I will talk about when I will have the symbol like C2, twice. What do I mean by twice continuously differentiable? Okay, this is a fact that if f is in C1, that means all the first order partial derivative exist and they are continuous, if and only if, you see just now I have explained gradient of f. Now that means gradient of f I can think about is a functions from a subset of Rn to Rn. Why? Because given f, suppose it is C1, that means all the first order partial derivative exists and continuous, then what is my gradient vector of f at x? Again, so this is of course a map from a subset of Rn, okay. This is a map from a subset of Rn to Rn. Why? Because x goes to gradient of f at x, and which is nothing but d1 f at x up to dn f at x, right. So that means given a functions f from S subset of Rn to R, I can think about that gradient function gradient of f, which is a map from Rn to Rn. That means x goes to gradient of f at x. It is continuous. So one side it is trivial, right? F is C1 means what? First order partial derivative exists and they are continuous. Now what is, look at the gradient functions expression. This is nothing but d1 of f at x up to dn of f at x, okay. F is C1 means first order partial derivative exists and they are continuous. That means each of the component function is continuous. So therefore this x goes to gradient of f at x is also continuous functions, right, because each of the component function is continuous. And what are the component function? First component is the partial derivative of f with respect to x1 variable, second component is partial derivative of f with respect to x2 variable, up to nth component is partial derivative of f with respect to nth variable, and each of the partial derivative continuous I assume because f is in C1. So therefore this function is continuous because component function is continuous, and therefore my function's gradient function is also continuous. Converse also true, because he assumed that del f it is continuous. So gradient of f is continuous means each component should be continuous functions. I already explained this kind of concepts in my earlier lectures when I talked about the continuity of a functions from Rn to Rm. It's a functions from Rn to R. So you have the n component functions, each of the function is continuous function, so therefore my given function is continuous. So now grad of f, it is a functions, it is continuous functions means each of the component function is continuous. And what are the component function? It is nothing but the first order partial derivative of f with respect to xi variable, each of them is continuous. So therefore it is by the definition that f has to be C1. That means I have a function f whose each first order partial derivative exists and they are continuous, and therefore f is in C1. So this is if and only. Now you kindly recall that if I have f is in C1, that means all the first order partial derivative exist and they are continuous. That means my function is differentiable because of the sufficient conditions of differentiability, if you remember. However, only differentiability will not implies that my function is C1, and that kind of examples you might have seen in my earlier lectures. That means, or maybe I'll explain in my next slides, that I'll show you that you have a function f which is differentiable but which is not in C1, because in C1 means I demand little more. So that means in C1 means not only I demand that first order partial derivative exists, but also that this first order partial derivative should also continuous. So that is the extra assumption. So it is expected if my function is differentiable, then in that case first order partial derivative exists. That's the theorem I already discussed. That means existence of total derivative implies existence of partial derivatives. But it may happen that first order partial derivative need not be continuous. So therefore, if one of the first order partial derivative is not continuous, then I can conclude that my function is not a C1. So this may be the case, and maybe in the next slides I'll have the example, I hope. Yeah, so first example I'm saying that, okay, consider a functions f from R2 to R. So these functions, this is a very nice function, it's a combination of polynomials and the exponential functions. So you have to check f is in C1. So you have to check whether the first order, so I have functions from R2 to R. So that means you just check del f del x and del f del y, and just see whether del f del x, again it's a map from R2 to R, and del f del y is again a map from R2 to R, whether these are continuous or not. That's very easy, right? So f is given like that, you easily calculate del f del x just by keeping the variable, second variable y is constant. You just take the derivative, think about it as a function of single variable x and perform the derivative. So what is my del f del x at the point xy? You can easily calculate, right? So this should be 2x, okay, and this should be e to the power xy times y. That's it, y square, because it's a constant, is 0. And what is del f del y at xy? So x square is a constant, so that means when I am talking about the partial derivative of f with respect to y variable, so keep x is constant. So the first one is 0, second one is e to the power xy times x and then 2y. Now both the first order partial derivative exist and they are also continuous, because what? It is a combination of polynomials or combinations of exponential and polynomials, right? And these are very nice functions, these are continuous functions. So therefore this is continuous, this is continuous. So therefore now for a given function say both the first order partial derivative exist and they are continuous. So therefore by the definitions that f has to be C1, that means f is a C1 map. However, consider this example. Here I can say that yes, in this example I will tell you that yes, my function is differentiable, but it is not C1. So you have to check that the function should be differentiable, right? Then first you check what you have to check. So I have a functions, look, functions from R2 to R is given. So if xy is non-zero 0, then it gives you that like x square plus y square times sine of 1 by x square plus y square, and at 0 0 is 0. So that means again it is a function which has a breaking point at the point 0 0. So that means to talk about or to calculate the first order partial derivative of f with respect to x variable and y variable, you just calculate at the break point using the definitions, and if xy is non-zero, it's a very nice function, right? It's a combination of polynomial of x and y and sine functions, and these functions are very nice function, differentiable function. So I can easily do that or perform the derivative. So that is why if I calculate it, it will be easy, right? First of all, if xy is non-zero, so I am just writing it here. So right, if xy is non-zero, then what will happen? Del f del x at the point xy, you just perform the derivative keeping y variable constant. So that means you have, this is the expression of your functions. If xy is non-zero, you just think about y is a constant and take the derivative with respect to x. Then what will happen? This is 2x times sine of 1 by x square plus y square, okay. And then what will happen? Then you have a x square plus y square, Leibniz rule, okay, it's a product of two functions. So this is cosine of 1 by x square plus y square, and then times 1 by x square plus y square whole square times 2x. So this is the expression. So if xy is non-zero, this is the expression of the first order partial derivative of f with respect to x variable at the point xy, xy is non-zero. So but you need to calculate del f del x at the point 0 0, but that you just use the principal definitions. And what is this? If I calculate it, this is nothing but limit h approaches to 0, f of h0 minus f of 0 0 divided by h, right? At the point 0 0 I want to talk about the partial derivative of f with respect to x variable. Now what is this? This is limit h approaches to 0, f of h0. Now f of h0, look here. So what is the value of f of h0? So that means y is 0, x is h. So that means it will give you actually h square sine 1 by h square, and f00 is 0 given, right, divided by h. What is this? This is limit h approaches to 0, h times sine 1 by h square. Now sine function is a bounded function, h approaches to 0, I am hitting with by h, so this limit has to be 0. So therefore I can have the partial derivative of f with respect to x variable at the point 0, 0, and what is this? This is actually 0 if the point xy is 0, 0. So now I have the expression of my first order partial derivative. It is exist at each point in R2, and if xy is non-zero, this is my expression, it's 0, and at the point 0, 0 it is 0. Similarly, you can calculate del f del y. If xy is non-zero, you just keep the x variable constant fixed and perform the derivative with respect to y variable. You will have some sort of expression like that, and of course you have to calculate del f del y at the point 0, 0. There you use the definitions, and of course if you calculate, I think you will end up with a similar conclusion that it should be 0. So therefore you have first order both partial derivative exist at each point, and then you have to talk about whether it is C1 or not. I am saying that it is not C1. That means you have to check that your one of the first order partial derivatives should not be continuous. Now once I have the expression of the first order partial derivatives, then you can talk about the continuity, right? And of course by looking at the expression of the first order partial derivatives, you have to just think about the continuity at the breaking point, because if my point is non-zero, it will be nice. It is a combination of polynomials, sine functions, cosine function. It will be continuous functions. So therefore just to talk about that, yes, my one of the first order partial derivative is not continuous, just check the continuity at the point 0, 0, because at the point 0, 0 it varies, because if it is not 0, it is very nice, it is a combination of polynomials, sine functions, and these are nice functions, these are continuous functions. So you have to just check the continuity of your one of the partial derivatives at the point 0, 0, and you will see that one of the partial derivative is not continuous, and therefore my function is not C1. However, my function is differentiable, I am saying. So differentiable means what? If you remember in my earlier lectures, I said that if I have a function from R2 to R, and suppose the partial derivative, suppose I want to talk about the differentiability of my f at a fixed point. So let it be 0, 0 here. So what you have to do, first you have to check the first order partial derivatives exist or not. So how many partial derivatives here? You have only two partial derivatives, first order, del f del x, del f del y. Suppose I want to talk about the differentiability or existence of total derivative at the point 0, 0. What you do? You first calculate the first order partial derivatives at the point 0, 0 and see the value. I already calculated del f del x at 0, 0, it is 0, and del f del y, if you calculate at 0, 0, it is again a 0. So therefore I have the vector, gradient vector, that means del f, that means gradient of f at 0, 0, this is exists. This is a what vector? This is a 0, 0 vector, that I know. But that does not mean that my function is differentiable or total derivative exists. So first you have to check the gradient vector at the point 0, 0, along with you have to calculate that limit of the quotient should be 0, if you remember. Then only I will say that yes, my function is differentiable, and that gradient of f at 0, 0 is nothing but the total derivative of f at the point 0, 0. So therefore gradient vector I have calculated, right? Del f gradient of f at 0, 0, which is nothing but del f del x at the point 0, 0, comma del f del y at the point 0, 0, and I just calculated this is 0, 0. Of course, I have calculated del f del x at the point 0, 0. You just calculate similarly del f del y at the point 0, 0. So this is actually 0, 0 vector. So that means this is okay. Now to conclude that my function is differentiable, I have to see whether the limit of the quotients of the norm should be 0. That means what I have to check? I have to check limit hk goes to 0, 0, because I want to check the differentiability of f at the point 0, 0. So what you have to do, if you go back and see the definitions, that means I have to calculate this limit of this f of h comma k minus f of 0, 0 minus gradient of f at 0, 0 acting on hk. This norm divided by norm of h comma k. So along with the existence of gradient vector at the point 0, 0, with this that this limit exists, that means not only exists, this should go to 0. If this is the case, then I will say that yes, my function is differentiable and derivative is this one. So how do I do that? So I have to show that this limit is exactly equal to 0, not only existence, it should be exactly equal to 0. You just calculate it. So limit hk goes to 0, 0. Now f of 0, 0 is 0 given, so that means you have f of hk. Now look, gradient vector is actually 0, 0 vector, and if I take the action on hk, then dot product, then it will again 0. So it will not contribute anything. That means I have to just calculate this now, this limit, and I have to see whether this is 0 or not. So what is this? This is same as limit hk goes to 0, 0. If hk is given, so what is this? You just write it. So this should be, I think, h square plus k square, then sine of 1 by h square plus k square, and what is the norm? Norm is square root of h square plus k square. That means what will happen? So that means this is nothing but I am trying to talk about hk goes to 0, 0 of square root of h square plus k square times sine of 1 by h square plus k square. Correct? Now what is this? This is a bounded functions. Sine of 1 divided by h square plus k is a bounded function, bounded by 1, and this is, see, I am hitting with by square root of h square plus k square. So this limit is what? This limit has to be 0. So therefore, what I conclude is that I have calculated first order partial derivative of f with respect to x variable and y variable at the point 0, 0. I concluded that yes, the gradient vector of f at 0, 0 is 0, 0 vector. Along with that, I have calculated the quotients of this limit, and I have to show that this is 0. If that is the case, then I will say that yes, my function is differentiable and the derivative, total derivative exists, and derivative is nothing but gradient of f at 0, 0, which is nothing but 0, 0. In this case, this is true. So that means my functions f is differentiable, that means the total derivative exists. However, my function is not in C1, that means one of the partial derivative of f is not continuous at the point 0, 0, because you have the expression of your partial derivative and the breaking point is 0, 0, because if the point is not 0, 0 point, then it is continuous. So only at the point 0, 0 you have to check, and you just kindly check that yes, either del f del x or del f del y is not continuous at the point 0, 0, and therefore it is not continuous in R2, and hence my function is not a C1, because if it is has to be C1, first order partial derivative exists and has to be continuous. That is the definitions. So this is one of the example. So here my function is differentiable, however f is not in C1 actually. That means for C1 I need little bit more than the existence of total derivative. That is what it says. Okay, so I just wanted to extend these notions little more. That means C1 part I said, and then I said that what will happen if I have the notion C2. Okay, C2 means, that means I want to talk about that my function is not only differentiable, first order derivative exists, I want to talk about the second order. So in that case, what will be the corresponding definitions? Look, what I said is that, so let S is an open subset of Rn. So f is a map from Rn to R. Suppose it is differentiable, so that once my function is differentiable, that means first order partial derivative exists. That means each di of f I can think about is a map from S subset of Rn to R. Now what I am saying is that if the partial derivatives, that means first order partial derivative djf exists at the point x naught, that means I have a functions. This is differentiable, that means first order partial derivative exists. Now first order partial derivative I can think about as a functions from a subset of Rn to R. Now I can talk about again the partial derivatives of my function djf or d1f, d2f, dnf. So that is why, so if the partial derivative of this function, I am not talking about the partial derivative of f, that is already there, right? Partial derivative of f exists because my function is differentiable. Now I want to talk about the partial derivative of these functions, djf. These also functions from a subset of Rn to R. That means I am talking about the second order partial derivative, that means dijf at x naught exist, then f is said to be have the second order partial derivatives at x naught. Yes, of course, if the first order partial derivative exists, that follows from the existence of the differentiability of f. On top of that, if I say that yes, if the partial derivatives of the first order partial derivatives exist, that means if the partial derivatives of djf exist for all j from 1 up to n, or in other words dijf at x naught exists, then I will say that f is said to have second order partial derivative at the point x naught. When I say that f is said to be in C2, in bracket I have written twice continuously differentiable, that means I demand that second order partial derivative of f at the point should exist. On top of that, I want that second order partial derivative, again I can think about which functions from a subset of Rn to R, it has to be continuous. Okay. So in C1 I demand that yes, first order partial derivative should exist and continuous. When I am talking about the C2, that means I want that second order partial derivative exist at the point and they should be continuous. Of course, when I am talking about the existence of second order partial derivatives, that means of course first order partial derivatives should exist and they should be continuous. In fact, they should be differentiable. Otherwise, I cannot talk about the existence of second order partial derivatives, right? Then first order partial derivative has to be differentiable. Then only I can talk about the existence of second order partial derivative. Along with, I demand that yes, the second order partial derivative I need, they also should be continuous. Then I will say that my function is in C2. Similarly, you can define Cn. So, that means I want the existence of nth order partial derivatives, along with that nth order partial derivative should be continuous. That is the meaning of Cn. So now you can just combine it. So, C1 means I want the existence of first order partial derivatives and the continuity of the first order partial derivatives. C2 means I want the existence of second order partial derivatives along with the continuity of the second order partial derivatives. In particular, if f is in Cn, then I will say that nth order partial derivative of f exists and they should be continuous. Okay. So, that is what I have written. Pth order partial derivatives of f are defined similarly. Similarly means, that means if I take about the nth order or pth order partial derivatives, that means that pth order partial derivative should exist and they should be continuous. Then only I say that my functions belongs to Cp. Okay. Parallel extension kind of things. Of course, you just keep in mind that when I am talking about the existence of second order partial derivatives and their continuity, by default my first order partial derivative exists and they are differentiable. Okay, that's you should always remember. Similarly, if I have the existence of nth order partial derivative, existence of nth order partial derivatives along with the continuity of nth order partial derivatives, that means if I come back to the one dimension less, that means if I want to talk about the existence of n minus 1th partial derivatives, that means they always should exist and has to be differentiable, otherwise I cannot talk about the nth order partial derivatives. Okay. So, that is already hidden in their information. Okay. Now, once I have these notions of say C1 function, C2 function or Cn functions, then I will have or I will introduce the notion of Hessian. What is this? So, what I am saying is that suppose you have a functions from Rn to R and suppose this is in C2. Now, I already introduced notion. C2 means what? C2 means, that means second order partial derivative of f exists and they should be continuous. That immediately implies that my gradient functions, which is again a functions from Rn to Rn, that means x goes to grad f of x, which is nothing but d1 fx up to dn fx. Okay, the gradient function, this should be differentiable and that is okay. Why? Because if I want to talk about the differentiability of a functions from Rn to Rn, and if you remember there is a theorem I have discussed that if I have a functions from Rn to Rn and if I write it as a component function, each of the component function is differentiable, that means my function is differentiable. So, now this is my gradient functions, these are the component functions and I have to just kind of convince you that yes, each of the component function is differentiable. In fact, this follows from the assumption that my function is C2. And what is C2 assumption? C2 assumption means my second order partial derivative should exist and they are continuous, right? Now, to talk about the existence of the differentiability of the component functions or to talk about the existence of differentiability of the first order partial derivative, say d1 fx. So, d1 fx or say I should say d1 of f, which is a map from say Rn to R, that means x goes to d1 fx. So, if I want to talk about the differentiability of this d1 of f, then what I have to do? I have to first say that yes, all the first order partial derivative exists and they are continuous, then only I can conclude that yes, d1 of f is differentiable, that means total derivative exists. Now, once I talk about the existence of partial derivative of the map d1 of f, that means what derivatives I am talking about? That means I am talking about the second order derivative. That means I want to talk about the derivative like d1 f comma d1 2f up to d1 f. So, that means to talk about the differentiability of the d1 f, that means first order partial derivative of f with respect to x1, so it is a map from Rn to R. And if I want to talk about the differentiability, that means you just consider the partial derivative of the map d1 f. And what are the partial derivatives of the map d1 f? This is nothing but the second order partial derivative. That means you just take the derivative of d1 f with respect to one variable x1, x2, xn. That means you want to talk about d1 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 f. So, that means this is nothing but the second order partial derivatives. And what is the assumption in C2? That means my second order derivative partial derivative should exist and they are continuous. Now, each of the d1 d1 to d1 n f, these are exist and they are continuous. So, since all the first order partial derivatives of my map d1 f exist and they are continuous, Therefore, by sufficient condition for differentiability confirms you or tell you that yes, the map D on F is actually differentiable, in other words total derivative exists. Okay? So, that means this is total differentiable, similarly your D2 and similarly your Dn. So, that is why the assumption F is in C2 is important. So, C2 is saying that the existence of second order partial derivatives along with the continuity. Now, to talk about the differentiability of the first order partial derivatives, I need the existence of the second order partial derivatives of the map D1, D2 and Dn, and they should be continuous, and that is automatically in the hypothesis that F is in C2, and hence each of the component functions of del F or gradient of F is differentiable, and hence my function gradient of F is differentiable. So, this is one of the fact. Once I have the differentiability of the gradient map del F, then I can talk about the Hessian. So, what I am saying is that suppose that my functions f of x y has second order partial derivative exists at the point x naught a b, then the matrix, of course, here I am talking about a map from R2 to R, okay, only two variable, earlier one is the Rn variable. So, if I have a map from R2 to R and suppose it is in C2, or in fact C2 is more strong assumption, just assume that f x y has second order partial derivative exists at the point x naught. So, I do not want the continuity of the second order partial derivatives, but I want the existence of the second order partial, that is I have written. Suppose that if x y has second order partial derivative exists at the point x naught, then this is the Hessian of f at x naught. What is this? This is nothing but dxx, that means the second order partial derivative of f at x naught, then dxy at fx naught, dyx at fx naught and dyyy at fx naught, or in other words same notation fxx, fxy, fyx and fyy. In other words, you will see this is nothing but, so because if I have a functions from R2 to R, right. So, that means in that case, so if I have a function, let me tell you this fact also, if I have a map from R2 to R, then what is my gradient map? This is a map from R2 to R2, right, just now here. And how it acts? So, if you say this is x comma y, it goes to what is that? This is d1 of f at x and d2 of f at y. Sorry, I think this is wrong. I should say this is the one. So, this should be, so it should be a map, right. So, gradient of f at x y, which is nothing but d1 of f at x y and then d2 of f at x y, right. So, this is your map. Now, what is this? So, this is nothing but look. So, I have d1, that means dx or fx, whatever it is, and this is d2 or dy. So, that means if I write it as, so if you, for your notation, if I write it dx f at xy and dy at fxy. So, that means what is this? Now, you can actually connect what I am trying to say. So, this is nothing but the matrix, Hessian matrix. See, gradient of f is a map from R2 to R2, and what are the components? First component is dx f at xy and second component is dy f at xy, right. So, now if I want to get the Jacobian matrix of this gradient functions, this is nothing but this one. That means first component you have dx. So, again I am performing the partial derivative with respect to x variable of dx and partial derivative with respect to y variable of dx at the point x naught. Similarly, look, this is the second component dy. I am considering the first derivative with respect to x variable of dy, and this is the second derivative, that means partial derivative with respect to y of the function dy. So, that means you have to remember in this way. So, first row you just considering the partial derivative with respect to x and y variable of the function dx. Second row, it is actually the partial derivative of x and y of the functions dy. So, that means actually I am talking about the Jacobian matrix of these functions, gradient functions, which is nothing but the Hessian matrix. So, therefore, I can write this is the Jacobian of the gradient functions f at the point x naught. So, this is same as your Hessian. Okay. So, now I think it is clear a bit that if I have a functions from R2 to R and suppose if second order partial derivative exists at the point x naught, then this is the corresponding Hessian h f at x naught, which is nothing but first dxs f at x naught, first row dxx f at x naught, dxy f at x naught, second row is dyx at f x naught, dyyy f at x naught, and this is the same notation. Instead of dxx I am just writing fxx or fxy. So, these are the notations you are familiar with, right. So, fxx means what? That means the second order partial derivative del 2f del x square. What is fxy? First you take the partial derivative of it with respect to x variable and then consider the partial derivative of y with respect to y variable or partial derivative of the function fx with respect to y variable. Similarly, fyx means what? You perform the partial derivative of f with respect to y variable, and then you perform the partial derivative of the functions fy with respect to x variable, and similarly this one. So, that is for R2 to R. In fact, I have written the Hessian matrix actually in Rn. So, that means if I have a S is an open set in Rn, and suppose f is a map from S subset of Rn to R, it is a scalar field, and suppose let f be twice differentiable at the point x naught. Okay. So, twice differentiable, that means that I am talking about the total differentiability, in other words that the existence of second order partial derivatives, suppose this is exist, then the Hessian matrix H of f at x naught is the matrix whose entries, that means if I want to write a matrix, if I give the ij element, then it will be enough. So, ij entry should be dijf at x naught. So, in other words, this is the corresponding Hessian matrix if I have a function f from subset S subset of Rn to R. So, that means if my function is suppose twice differentiable, I demand like twice differentiable means of course first order partial derivative and second order partial derivative they exist. Once second order partial derivative exists, then I can form the matrix whose ijth elementaries are dijf x naught. This is called the Hessian matrix. Like the earlier slides I have shown, if I have a function from R2 to R, what is the corresponding Hessian. Now, the second order derivative of f x naught, which I denoted, of course you remember these notations I have already used, f double prime and x naught. It is a function from Rn to R. So, now total derivatives, as I said, it is a linear map from Rn to R. So, since it is a linear map, so that means since f double prime x naught is a linear map from Rn to R, that means if I act on some vector h here, okay, so or x here, it should give some real number, right. That means f double prime x naught is a acting on x, it should be a real number. And how it that? So, you can write it. So, I mean this is a linear transformations from Rn to R. If it acts on the vector capital X, it is an element in Rn. So, this is the one. So, that means x transpose Hx. Okay. So, what I am saying that x transpose means this is the row vector x1, x2, xn in Rn. So, what is H? So, H is the matrix Hessian matrix. It should act on a vector x. So, now what is H? My H dimension is H is a Hx. So, so that means H order is what? N cross n, and it should act on x. What is the element? X is vector. So, it should be n cross 1, that means column vector n cross 1. Okay. So, what is the Hx, what it will give? It will be a vector, again it is a vector n cross 1, okay, and x transpose is a 1 cross n. So, you will have xt Hx. So, that means xt which is a vector 1 cross n acting on a vector n cross 1. So, that means it is 1 cross 1, that means it will give a scalar. So, this is the action. So, if I once I have a function f which is twice differentiable, I know what is the notion of Hessian matrix. Once I have the Hessian matrix, then since my function is twice differentiable, that means the total derivative exists, that means f double prime x naught, it is a linear transformation from Rn to R, and I can write the actions of the linear transformation on some vector x in Rn in terms of the Hessian matrix, which is nothing but x transpose Hx, where xt is nothing but the row vector x1, x2, xn in Rn. So, that is the connection. That means that the action of the linear transformation, how it acts in terms of the Hessian matrix. Now, look, there is a note say that if the second order partial derivatives of f are continuous. So, now to talk about the Hessian matrix, as I said, I just need the existence of the second order partial derivatives. Of course, I do not need the continuity of the second order partial derivatives, only the existence of second order partial derivative at the point x naught. I know the notions or concept of Hessian matrix. Now, on top of that, if I assume that second order partial derivatives not only exist, they are also continuous, then you can guess what I am trying to say, because I have already a mixed derivatives theorem. If all the second order partial derivative exists and they are continuous, then the second order mixed derivatives, their value should be equal, right. So, look, if the second order partial derivatives of f are continuous at the point x naught, then the mixed partial derivatives, that means dijf and djif are equal at the point x naught. Now, look at the matrix, Hessian matrix. What are the diagonal? Diagonal are d11f, d22f, dnnf, and what are the off diagonal? So, that means look at this one, d1n and dn1. If I assume that my only second order partial derivative exists, then I do not know whether these two values are equal or not. That I do not know. I have already provided few examples. So, just existence of second order partial derivatives will not tell you their equality. However, if the second order partial derivative exists and they are continuous, then mixed derivatives, they are actually equal. That means in that case, d1nf at x naught is exactly equal to dn1f at x naught. right. So, in other words, except diagonal, all the off diagonal they are equal. That means d1 to f x naught is exact. In other words, what I am trying to say is that dij f at x naught is exactly equal to dji f at x naught. Okay. Now, if I have a matrix aij, so and okay, then I say that okay. So, in other words, if I have a matrix aij such that aij is exactly equal to a ji, then those matrix I will say that it is a what is called symmetric matrix. So, that means so the Hessian matrix will be a symmetric matrix, that is H exactly equal to transpose of H. That means if I have a matrix A, I think you people know aij, okay, this is a matrix. If this is true that aij is equal to aji, then I will say that yes, my matrix actually symmetric matrix, okay. And this is exactly equal to transpose. Transpose you know, right. If I have a matrix A, you can define the matrix A transpose either AT or a small t. Suppose this is Bij, okay. And what is the connection between Bij and the element of Aij? So, Bij is nothing but Aji. So, given a matrix A whose component is ijth component is small aij, then you can have a concept of the transpose matrix AT. If I write it as Bij, the relation is that Bij is nothing but Aji. Now, if A is equal to A transpose, that means it's a symmetric matrix. That means if for the matrix, the property should be that Aij, small a suffix ij should be Aji, and which is true in this case, because if I assume that my second order partial derivative also continuous, that means the mixed partial derivatives value should be equal, and then the Hessian matrix in that case actually symmetric matrix. Okay. So, I just say this one, this is a fact I already explained. Okay. So, Hessian, so facts, if I have a functions f from Rn to R which is C2, that means twice continuously differentiable, that means second order partial derivative exists and continuous. I just explained that the Hessian in that case it will be a symmetric matrix, and I already explained that what is the Hessian matrix for R2 to R, which is nothing but the Jacobian matrix of the gradient vector. So, that is why I have written. So, if my function is in C2, then it is symmetric, and the Hessian matrix of f at x naught, which is nothing but the Jacobian matrix of the gradient at the point x naught. This is the Jacobian of gradient of f at x naught. So, I already explained. So, gradient of f, so given a function f from Rn to R, gradient of f is a map from Rn to Rn, okay, and how it acts. So, x goes to gradient of f at x, and what is this? This is nothing but d1 f at x up to dn f at x, okay, right. So, these are the component functions Rn to Rn, and if I have a functions from Rn to Rn, and if suppose if my function is differentiable, then the total derivative exists. And what is the total derivative? Total derivative, it will be a linear transformation from Rn to Rn, it will have a matrix representation, and that matrix representation I already explained is the Jacobian of this map. So, now Jacobian of this gradient vector or gradient functions get grad f at x naught, which is nothing but this matrix, Hessian matrix. Okay. So, in that case the Hessian matrix, which is nothing but the Jacobian matrix of the gradient functions grad f at x naught, and it is actually symmetric matrix because I assume that C2. That means it is twice continuously differentiable, that means second order partial derivative exists and they are continuous. This is one simple example I have given. So, f of xy is equal to these functions, you just calculate that Hessian. So, just what is my functions? You have to just calculate fx, fy, and that means this is fxx, fxy, fyx, fy. This is the just very simple calculation. This function is polynomial in x and y, and this is the matrix you will get. And you see, so this is actually symmetric matrix because aij is equal to aji, because just look at the functions. Your function is what is my fx? Fx is nothing but, here fx is nothing but what? 2x minus 2y. And what is my fy? Fy is nothing but minus 2x plus 2y. So, I have fx, fy, they are very nice function, they are continuous function. Okay, first order partial derivatives. What is fxx? This is 2. What is fxy? So, that means this is again minus 2. What is fyy? This is 2, and what is fyx? That is minus 2. So, all are constant. So, that means all the second order partial derivative exists and they are continuous. That means my function is in C2. So, therefore, the Hessian matrix should be symmetric, and that exactly going on here. Okay. So, I think I should stop here. So, now what I have done, I have introduced the notion of the symbol C1, C2 and Cn. So, C1 means first order partial derivative exists and they are continuous, C2 means second order partial derivative exists, all second order partial derivative exists and they are continuous. Similarly, you have a Cn, all the nth order partial derivatives and continuous, then I will say that my function is in Cn. Once I have the function from Rn to R, then I can think about my function's gradient of f is a function from Rn to Rn. Then if I say that the given f, if I ensure you that yes, gradient of f is also differentiable, then there will be a what is called Jacobian matrix corresponding that gradient functions grad of f, and which is nothing but the Hessian matrix of my f. Okay, and if I assume that my functions Rn to R is C2 functions, then your Hessian matrix or the Jacobian matrix of the gradient functions f, gradient of f, it's actually a symmetric matrix. Okay, so I think that that's all about the concept of Hessian, and of course once I have the notion of Hessian, then you can have the actions of your total derivative at some vector in terms of the Hessian matrix. So, these are the concepts I have discussed. In my next lecture, I will talk about the concept of mean value theorem and Taylor's theorem. Thank you.